Hi, welcome to this lesson on Euclidean geometry, ratios and proportions. Let's have a look at a revision of proportions in polygons. So we start off with the definition. A polygon is a two-dimensional shape that consists of three or more straight line segments that close the shape in the plane. So here's some examples of planes that are shown below here. Okay, so this rectangle, right, is a polygon in the plane. This triangle is a polygon. This trapezium, this pentagon, this hexagon, and this diamond or kite. All right, so these are examples of some polygons. So let us recall the fundamental quadrilateral shapes, because these consist of many important properties, geometrical properties that we can utilize when we are solving geometrical problems. So there's the square, the rectangle, the rhombus, parallelogram, trapezium, and kite. So let's revise the basic properties of each of these quadrilaterals and then practice an example regarding proportions using these quadrilaterals. So to summarize again, a square essentially is a four-sided polygon, right? Quadrilateral, where all side lengths are equal. So this side length S is equal to every other side length here. The diagonals bisect the square and intersect at 90 degrees. There's right angles, four right angles in the interior of the square. It also bisects those right angles into 45-degree angles, and opposite pairs of sides are parallel. Rectangles, okay, these are sort of like squished out squares, right? Where in the fact that they also have four 90-degree angles. The diagonal lines will also bisect each other, right? And it'll actually create two congruent triangles, right? Right angles, so we've mentioned that they all have four interior 90 degrees and opposite pairs of sides are equal and parallel to each other. Then we have the rhombus, which is also like a square, but it's been more squished sideways, right? So all sides are equal, just like the square, but this time the interior angles don't need to be all 90 degrees, but the opposite angles are definitely equal to each other, so that's important. The diagonals will also bisect each other at a 90-degree angle, and the opposite pairs of sides are parallel as well. Then we have a parallelogram, which is sort of like a rhombus but a bit extended out in that it has opposite pairs of sides equal in length and parallel. The diagonals will bisect each other and opposite pairs of angles are also equal. So all these properties that we're going through are really important when it comes to things like parallel lines, equal side lengths, because all of these end up creating either similar or congruent shapes. And what we usually deconstruct polygons into as best we can are triangles. And that's why we focus a lot on the similarity and congruency properties of triangles. Then we have a trapezium, which is a quadrilateral where only two pairs of sides, so that's in this case A, B, and DC, are parallel to each other, and then the two opposite pairs do not need to be parallel. Okay, all four side lengths do not have to be equal to each other, and again, diagonals don't necessarily bisect each other. Okay, and then lastly we have the kites in the case where adjacent sides are equal, so AD and BC are equal in length, and then DC and BC are equal in length. Also, the diagonals cut the kite into two pairs of congruent triangles as seen in the diagram, where it also bisects at 90 degrees, and the shorter section of the diagonal is cut into equal pieces. All right, so that is an important revision of the quadrilaterals and their properties. Let's have a look at an example. So ABCD is a rhombus, and we're given that BD, this diagonal length here, is 16 centimeters, and the ratio of AB to BD is 3:4. So now we want to calculate the following to two decimal places and provide reasons. The length of AB. So because we're given this ratio here, AB to BD is 3/4, we can manipulate that algebraically into the following equality here. So AB divided by BD is the same as 3 divided by 4. So we're looking for the length AB, so I'm going to cross multiply both sides by BD to get this equation. But we were given the length of BD. It was 16 centimeters, right? So 3/4 of 16, when you multiply that out, gives you 12 centimeters. So this length here is 12 centimeters. And because we know it's a rhombus, that means every side here is 12 centimeters, because that's the important property of a rhombus, right? opposite pairs of sides are parallel and all sides are equal in length. Okay, what about the length of AO? So this diagonal piece here. Well, we calculated these side lengths, 12 centimeters each. And we know the full length of BD is 16 centimeters. So again, by the properties of a rhombus, the diagonals bisect each other. So what does that mean? That means because they bisect, bi meaning two or half, and sect cutting, so cutting into two equal pieces, that means BO equals OD. So both of these must be 8 centimeters, since we were given that the total length was 16 centimeters. We also know that AB is 12 centimeters from the previous question. And now we have a right angle triangle where the hypotenuse is 12 centimeters and an adjacent side is 8 centimeters. So if we use the Pythagorean theorem, we can solve for AO. So we get AO squared plus BO squared equals AB squared. We substitute the values in and we get an answer of 8.94 centimeters for the length of AO. All right, so that means that's 8.94 centimeters, and therefore by the properties of a rhombus, that means this side as well is 8.94 centimeters. So you can see these two sides are equal because they bisect each other, and BO is equal to OD because it bisects as well. Lastly, what is the area of the rhombus ABCD? So let's notice something. If we look at triangle ABD, this one here, then that's going to be congruent to triangle CDB by side, 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 because this is 12 centimeters, and 16 centimeters, and the same thing here, 12 centimeters, 12 centimeters. So we have a congruency. So therefore the area of the total rhombus is going to be just the area of the one of the triangles multiplied by 2. So let's look at the area of triangle ABD. Right, it's going to be half times the base, which is BD, times the perpendicular height of AO. But we worked out AO. It was this value here, 4 root 5. So we plug that in. So the area of this rhombus is going to be 2 amounts of this triangle area. So that's what we've got there. So 2 goes into a half exactly once. So we just have 1 times BD times AO, where BD was 16 centimeters. That was 4 root 5 centimeters. Multiplying that out, we get 143.11 square centimeters. Do not forget to put the unit measurements, right? Because now we're looking at area. Area is a 2-dimensional construct because it deals with a length and a width. Right. So that is how we would do these types of questions. I'll see you in the next one.